Good morning, everyone. Thanks, organizer, for giving me opportunity to present our work in this nice meeting. So here I will mainly talk about the Berry curvature induced optical bistability. So as you have heard in the morning session also, and the very latest talk by Subro also, that how Berry curvature is very important and how it can explain a very fascinating phenomena related to the transport, optical, linear and non-linear, all those things. So here I will talk little bit on it, that how Berry curvature can also play a role to induce a optical bistability, and I will also tell that what is meant by optical bistability in a coming slide. So this is our group at SRM. So we are mainly working in the different domains, linear, non-linear, which I will talk on the non-linear here, and then topological effects. My student has already shown in the poster session, and hydrodynamic, that also shown by student, and then first principle investigation, oral presentation has been given by Narayanan on the altermagnetism. So I will mainly talk on this very recent work, which came into yesterday only in PRB. And this work is completely done by our UG student, and who is now intern in Taiwan. So the outline of my talk is, first I will explain on the about the optical bistability, what does it mean and how it is important, and what is the principle behind to observe the optical bistability, and what is the literature or traditional method people have followed to explore the bistability, and then what is the key physics behind it. Then I will move towards a new setup, that alternative route that we have proposed to get an optical bistability by knowing that the importance of the Berry curvature and the non-linear effects. And then we will apply our theory to one of the system, very well known, this is a Weil semi-metal system, time reversal broken system. And then we will explain that what are the feasibility regions where we can get such type of feature, and then I will conclude. So first, let's say what is optical bistability. Optical bistability is just optical phenomena. You are giving a one input intensity, but you are getting a two output. Out of it. So as you can see that you are giving an input intensity, so you have a system and you are getting two output. And if we make a plot for this incident intensity and the transmitted, you can see that there is a very small incident intensity. This is a monotonic, but when you are increasing, so at certain point of threshold, it will jump to the other way, and if you start decreasing again, it will jump. So this way it will make a S-wave shape or a hysteresis loop type of structure it will obtain, which clearly gives that how this bistable nature can helpful in the bistable devices, optoelectronic devices. So that's way one can say that how the light can be controlled by the light. So there are traditionally methods what people have discussed, that's very early days, 1984, 1976. People used to take this optical non-linearity, which they say that you modulate the refractive index or absorption coefficient. By increasing the intensity, your refractive index will change, and automatically then you will get the non-linearity within the system. And you also get a feedback, because this is not depending only on your current intensity, it depends upon the feedback mechanism. So they used a cavity, optical cavity, where they send a light and multiple reflection happens across the sample, and then they increase the transmission and then get the two points. However, in that we can see that this stability, optical bistability only occurs in the includes a dissipative part. So that means, but we now in the scenario that we are mainly looking for the non-dissipative things. So the question, the drawback this comes as that because of the energy losses happens due to this phenomena, one has to look for the another way or alternative method that one can explore, that how one can reach the non-dissipative part. And the question arises that can we have a other way to get, or can we have a optical bistability on an alternate route which can give rise to a non-dissipative type of things, and one can reduce the energy losses. So the big answer is yes, because we are well known now about the transverse responses, and when we have a rective transverse response, one can avoid this power dissipation issues and one can get such type of phenomena. So in that also you don't need a cavity type of structure which will give the multiple reflection, again those type of things that can be avoided. So if you look this schematic, so you send a light, sample will give you are sending a light and measuring taking a current along perpendicular to that field, you calculate this Hall current, and you get a transmitted light out of it. So if you see here that Hall current is proportional to the sigma xye, which you have seen in the previous talk as well. So both are perpendicular to each other. When you take a dot product, this also indicates that there's no power dissipation happens when you take into this picture. So the recipe is that if you have a system which has a finite Berry curvature, so when we have finite Berry curvature, then you will get an anomalous response out of it. Then getting an anomalous response, you apply the Maxwell boundary equations, which will play a role as a feedback mechanism to get other part of things, and then you can get a optical bistability. So going into that direction, so let's move to our setup that we have developed to approach this problem. So assume that you have a sample, that's a 2D sheet, and you have placed into xy plane at z equal to 0 interface. You are sending a light, and you are getting some reflection and the transmission out of it. You apply a you are applying the Maxwell relations at the boundaries. You can see that there is a continuity of this electric field. The left and right will be same, and magnetic field will follow and it depends upon the amount of the surface current across the sample. Now using this relation and applying the Faraday law, you can come to this type of algebraic equations. So what you can see here is that this whole story depends upon the J, that's the surface current. And when we look for this linear response, which is J equals to sigma E, that the transmission and the incident, they will follow the linear behavior. However, when you go to the non-linear, it will not tend to be linear because of non-linearity. So here we have taken about a third order, we have not taken the second order because of the symmetric constraint. Second order can be, in centrosymmetric systems, and second order is not allowed, so that's why we have not taken into account. In general, if we expand in the terms of field, one has to take all the responses, order of responses. So going further, when we have a response, this current relation for the isotropic system, especially with the time reversal symmetric system, we are mainly focused on time reversal because we want to look into the Berry curvature induced part. So we have only focused on certain response tensor components only. One can get write the equation for this current in the terms of the response and the field, and plug back into this boundary condition, and one can write such type of equation. Now taking what type of light we are taking, the circularly polarized light, that because the x and y both have some phase difference will be there, so then one can also end up with this nice relation which will help us to get the optical bistability relation. So if you go there, from this equation, we can see that if we take the norm of this equation, mu naught is the permeability, c is the speed of light. You can get the input-output relation, and you can clearly see that this is a third order, this is a cubic equation in the T, transmission intensity, which gives us a 3 different solution, out of which 2 will be a stable and 1 will be a unstable solution. And then I is a mod of this incident intensity square, and the transmission is for the transmitted field square. Now this main role here in this equation is mainly played by the 2 parameters which we call as the bistability parameter, which are beta and the lambda. And those parameters depend on the response. So beta depends upon the linear response, that's an anomalous Hall response, which we know that depends on the Berry curvature, and then lambda, which is the ratio of the third order to the first order response. By knowing this scenario, mathematically one can get an idea that what is the region or what is the value that we should need to get this nature. So to get this one, we have figured out that the beta, which sets that the curvature of this S type of curvature, so beta should be greater than 3. If you are within that limit, then you can get this feature. Another point is that when lambda, this ratio is less than 0, which defines that this feature will be observed, then you can get the bistability nature. So in short, if I say, if these 2 conditions satisfied in your system, whatever system you consider in your study, So if these two conditions satisfy, you can expect that the bistability behavior. Depending on the other conditions that the experimentally feasibility or the how much range parameters that you can take into account. Now based on this one, so we first now let's see that how one response can be taken into account. So here Shubhro has also discovered semi-classical transport. So this is the one slide I will only show, I will not talk much on it. So that which tells us how the time evolution of the distribution function, which has a drift part and the collision part. And the collision tells that here we have taken under the relaxation time approximation. And when we expand this distribution function in the terms of the field of the higher order power of the field in the perturbative limit, then one can plug back and one can get this scenario and plug back into the equation, the normal current equation, J equals to trace of velocity and the distribution function. So when we have a velocity which has two parts, group velocity and the anomalous velocity, we are mainly focused on anomalous. So anomalous velocity and the distribution function leads to the different order of response, first order and the third order response into the picture. So you need a system. Now this is for the high frequency, because the optical bistability we are working in the high frequency limit. You need a system again as it depends on the Berry curvature. So to test this one, we have taken this TRS broken wire semi-metal system. We have taken this low band model, two band model system, where is a chi is a chirality, Fermi velocity, V is Fermi velocity, sigma is a Pauli matrix in orbital basis, k is wave vector, and the q is in the momentum shift. So one can get the Berry curvature, and here if we take that the shift along the z axis, so b kz hat, one can get this linear order and the third order response, which tells us that it depends upon the while not separation. B is a while not separation parameter. So after getting this information, if you plug back into the bistability parameter, which we have seen that beta depends upon the linear response, one can see that this beta is depending upon the while not separation and also depends upon the sample thickness. And another thing is that our ratio of this third order to the first order response, that depends upon only the chemical potential. It is independent of the while not separation. So that means by tuning this sample thickness and the chemical potential, we can also play with these two parameters, beta and the lambda. So if we see in these plots that transmission versus the transmitted intensity and the incident intensity, we can see that when you increase the chemical potential, for example here 10 to 14 we have shown. So you can see that when going from the blue to this green curve, you can see that more and more intensity, this I is required. Why it is so? When you are increasing the chemical potential, you are moving away from the while not separation, while not points. When you are moving away from point, so then your third order response will become weaker and weaker. And due to that, your feedback mechanism will have to pay something. So for that you need a high intensity. So that's why for this high mu you need a high intensity to get this bistability nature. On the other hand, when you go with this the sample thickness from 1 to let's say 1.2 micrometer range, here also we can see that when you increase this d, the sample thickness, the parameter beta, which we have put a condition that beta should be greater than 3 and it depends upon the sample thickness. So that will become more, that means it will increase the linear response, that the contribution comes from the linear response part only, and however for this downfall will not change much in that picture. Now getting this one, so what are the feasible region that one can look to observe this optical bistability nature phenomena? So based on the condition beta is greater than 3, one can impose a lower bound on the thickness, which here we have put the condition for this while case only. So one can see that depending on this relation, that within this range the bistability nature is possible. However, based on then look into the experimental perspective, that what is the range for the system, like for this TAS, people have experimentally it is in the range of 0.05 to 0.3 angstrom inverse. Based on that, we can say that okay, bistability window is accessible for the realistic film thickness when the D is of the range of 0.5 to 5 micrometer. So I can, in short, I can say that here, so to get the optical bistability, you need time reversal symmetry broken. If we want to the anomalous part, however, other things can also be taken into account, other responses. Here we have only taken to the interband picture. We have not taken, we have not taken the kinetic theory part. We have only based on the Boltzmann approach, which does not take into account this interband, because our idea is to see that how the optical bistability, or what is the alternative route one can look for the optical bistability, rather than going to the interband contributions into it. So with this I will conclude. So then traditionally one can get the optical bistability by changing the refractive index or absorption coefficient, but in the new mechanism one can go into non-dissipative parts. So we do not need a cavity, but feedback can be taken into account by applying the Maxwell boundary condition at the surface, and experimentally also one can, why it is viable, by taking the field of 1 megavolt per meter in this range, and it can be tuned with the sample thickness and the chemical potential. So with this I thank the funding agency. Thank you.
Questions? Sir, in third order, you have only considered this intrinsic component. So there will be other component also, right? Extrinsic. So how they are?
We are in the very high frequency region, so that's why we can safely ignore the extrinsic part, which will play major role around the low frequency range.
Okay. Thank you.
Any other questions?
So how robust do you think is this bistable response against like disorder, finite temperature, dephasing, like all these kind of things?
Okay, so to look about the robustness about this bistability, then one can look about the temperature effects, as you are seeing the disorder contributions. But disorder contribution, all those things will major play a role again, and as I said that in the low frequency domains mostly. So if you want to look in the low frequency range, that means you have to also look into the frequency. Here we look on the terahertz range 1 to 3, I guess. We have look into that. So you have to go into the more low frequency range to get those type of feature. But I guess then bistability needs high frequency things. Other features can play, but physics wise it will not change much. Physics will not change. The condition that we impose beta on the lambda, those things will not change. Those conditions will remain same. You can tune in between to get those type of things. That is possible.
So if I understand correctly, your sample is just a monolayer of your this thing, and the incident light is perpendicular onto it. So is it not experimentally challenging for this single layer and doing it, experimentally measure it? And second is, does it depend upon any angle of the incidence? How does your comment will be?
Okay, so angle part can be taken into it. The only difference that I have seen that when you have a circularly light without angle, you just take only that pi by 2 phase change is taken into account. You have to be taken care into account that whether you are taking the real part of the conductivity or imaginary part, because we want purely reactive part. So if you go to the other parts, then then dissipation things will come into picture also, because when you take imaginary part, that cannot be taken as a purely reactive part. So that problem will come definitely. But it's correct that if you go to the more I can say that the like elliptically type of field or things, that can be more robust, I can say that here circularly, just to avoid that I can say complexity of that scenario.
And the experimental part, that monolayer of your
Okay, so yeah, so that's also correct question, that monolayer, if I go to the bilayer, trilayer, so many things that if you things, so that's just that can also be taken into account. So here that the framework that beta, those conditions which I impose beta greater than 3 or lambda less than 0, those conditions again irrespective of your material is monolayer or bilayer or whatever the things, you can convert those things into later into this one. For example, if we have taken a Y, which is a 3D, right? But we have imposed that the surface current, we convert into this 2D things and surface current, and we bring it and then transform into this our system. So that way one can do, but the conditions will not change at all.
Okay, so please thank the speaker. Okay.
The lambda is the ratio of linear conductivity and the third order conductivity, right? And it has to be negative. So then they should be of opposite sign.
Yes.
How to make sure that they are of opposite sign? This is the first question. And the second question is, what is the order of lambda? Because it is the ratio of first order and the third order. Then I would expect it will be very small.
That's why the lambda is less than 0 I have written.
Yeah, and why it is negative?
Okay, so if you take positive, right, for example, if you, let's take this equation, okay, forget about you have a sigma and just want to play with this equation to get the solution or this type of signature. You take lambda positive, for example, what you will see that this equation, you will not get the such type of bistable nature. Only the condition when you have a lambda is negative, that means when these two are in this opposite eigenvalue, the sign change is there in the third order and first order, only in that case that can be happen. And if I see that this one here, so here also you can see that sign change will come when you convert into this okay, I think I have not written, but yeah, so that will come. Okay, so you can see here also the sign change is there.
Okay. So please thank the speaker again.